10 years ago, I presented at the very first GopherCon about this side project of mine called Ngrok that I had built in a hot new programming language called Go. And since that groundbreaking talk, the Go community has anxiously been awaiting the sequel. Hungry for it, they filled the GoLang Nuts mailing list with fan fiction, expanding the GopherCon cinematic universe. And today, I'm pleased to announce the long-awaited second chapter of that summer blockbuster hit. That's not a very good title. Hello, GopherCon. My name is Alan Shreve. I'm incontrovertible on the internet. I am the founder and CEO of Ngrok, and it is a privilege to be here today with all of you. I may have been exaggerating a bit in that introduction. The title of today's talk is actually a 10-year retrospective on building an infrastructure service in Go. The talk I'm presenting today is born out of what happened since that first GopherCon. See, 2014 was a very interesting year for me because that little side project that I was working on became software that has touched millions of developers all around the world. Hands up if you've used Ngrok. Yeah, awesome. So today I really wanted to kind of like go back and use this as an opportunity for a retrospective on what I've learned in the last 10 years. Ngrok is now what I build full time, and it is written in Go. That means I've actively been working on the same Go code base for over 10 years at this point, which I think puts it in pretty rare company just out of sheer longevity of the project. It was first compiled on Go 1.3, and I think we're approaching like 1.23 or something now. So I wanted to talk to you today about what I've learned building Ngrok, but first, we need a little bit of context. So I want to first talk about what has changed. Not for Go, that would be too much, and reading change logs is maybe not the most exciting thing to spend our time on, but rather like what has changed for Ngrok and the Go codebase that I work on. So over 10 years ago, I launched an open source project called Ngrok with a hosted SaaS component to solve two initial problems. One was to make webhook development faster, and the other was to be able to demo code without deploying it. When I was a software engineer at Twilio, I encountered a problem. Twilio's web service wanted to notify me when it received a phone call or text message by sending me an API request. This meant I had to give Twilio a public URL for my API server, but the problem was that my laptop did not have a public URL. So that meant that if I wanted to test my code, I had to instead deploy my code to a server on the public internet. And deploying, depending on how good your infrastructure is, can sometimes take minutes, hours in worst cases, which is much too long to develop quickly. So I built Ngrok to solve that problem. You download a single executable written in Go, and you run a single command. When you do, you point it at the port that your local web server is running at, 80 in this example, and then you get a public URL for the API running on your laptop, which means you can receive HTTP traffic from the internet without deploying. This initial innovation was really how Ngrok became an API gateway for applications running anywhere, including your laptop. Today, Ngrok is a lot more. In addition to delivering apps on your laptop, it delivers production APIs and applications all around the world, running in clouds, running on-prem. We have expanded its power to not only put applications online, but to also combine all the functionality that you expect out of an API gateway and a firewall, a load balancer, a global delivery network into just that one single command. That means that Ngrok is a lot more powerful than it was many years ago. But we have tried to keep the same simple user experience for it. This is essentially that same original command that worked 10 years ago with an additional flag where you can specify a whole bunch of instructions to push rate limiting to our global network edge or block requests that are over a certain size, things like that. And since we're at a Go conference, I would also mention that we have also added like a Go SDK to it. So all of that stuff that you did on the command line, you can also do natively in Go. This is the standard Hello World web server that you're probably accustomed to in Go. With the Ngrok SDK, you just basically get a net listener. It's basically what we did was we turned ngrok into like a global ingress proxy that becomes a net listener inside of your Go application. So you can plug it into any Go software that uses net listener and have it put on the internet securely. In this case, we're like adding Google OAuth in front of it, but it'll show up just as another web server on the internet. I told you all of that really to see like just how much, like in order to do that, we had to write a lot of software, right? Like a lot. And we wrote it all in Go. And reflecting on building all of that software, I wanted to share with you a number of things that I've learned over the years. And while I have many lessons from growing and scaling ngrok, we have a short amount of time, so I'm going to focus on the ones that are like very specific to building Go code bases. Some of it will be some more practical in the weeds stuff, and some of it will be a little more abstract and high level. First, let's check in on what we were talking about 10 years ago. This was the agenda for my talk 10 years ago. It was what was on my mind was how do you like basically distribute Go applications out into the world. I think ngrok was one of the first kind of like command line applications that was like widely distributed in Go to many, many different users. And so things that were on my mind were like, how do I embed assets into the executable? That was hard. Today it's easy. There's a standard library package for it called embed. I had to figure out how to cross-compile it with CGO because a lot of the standard library relied on CGO. These days we have a native Go resolver, and the OS user functions all are native Go, so you don't have to worry about that stuff anymore. Terminal UX has come a long way. We have great libraries in the ecosystem for doing that. Crash reporting was something that I wanted to be able to like know when it crashed and send me a report of it. We still haven't solved that. Turns out it's a hard problem. And the last one is like how to get it to auto update. I built a service and a library to do that, and others have forked it and extended it. If you're interested in like kind of the CNCF way to do it, you want to look at Go Tough, which is kind of like a very secure version of an update framework. Let's talk about some of the more practical concerns in Go that we've like dealt with over the last, that we've been like using as we've built ngrok over the last 10 years. One of which is working with SQL databases. Most everyone has to talk to a database at some point or another, and ngrok has to do that all the time. When I started building ngrok, database SQL was really so painful that I actually wrote the stuff that talked to the database in an entirely different language. Like coming from Python and SQL Alchemy, working with Go was so painful that I was like, I'm just actually not going to do this. I switched to SQLX eventually, which was a much better improvement, but still error prone. And these days we use SQL C. While we were working together, myself and the author of SQL C, Kyle, I was very frequently complaining about how painful it was to write services that talk to SQL and Go, and he came back and built SQL C. The way it works is you write SQL, you run SQL C generate pointed at those files, and then it generates type-safe interfaces to your databases. So then you can call that code by basically it generates a function for every query that you wrote, and they are all type-safe, so you just simply like call those and pass in the types that you want. You don't have to work with database SQL or anything like that. It's very nice. It's really great because it's impossible to write queries that reference columns that don't exist. It is a type-safe interface to your database. When all of your SQL queries are pulled out of the application like that, it also means that you can do cool stuff like we do, which is we run lints on every single query where it checks to see if it table scans during CI by basically checking every single query against the database. Another thing that has changed a lot over the last 10 years has been RPC. Whether you have microservices or macro services, at some point you're probably talking to someone else. Like I said at the beginning, like ngrok had that Python service, and so there needed to be like actual like RPC between those two pieces. That initial communication was HTTP JSON, very common. Really ended up finding out that there were too many places where we ended up with like runtime errors, basically because the JSON changed shape and we didn't know, things like that. Moving to a more robust RPC framework has allowed ngrok to move and scale much larger and move much faster. There was a time in the middle where I tried Thrift. That did not work so well. The tooling was not great at the time. Maybe better now, but the kind of like preferred thing in the Go ecosystem, and kind of widely is gRPC. gRPC is fantastic. You should use it. We started using it in 2015. Use gRPC or Connect RPC if you would like from our friends at Buff. Ngrok has been using gRPC for 9 years, which I think also makes us one of the earliest adopters of gRPC. In addition to Go and SQL-C, we have over 100 gRPC services, and it's used for every piece of communication between all services. All like inter-service communication happens over gRPC. We actually take it a little bit further into like interesting ways. The most interesting is that our like dashboard and our internal interfaces actually speak gRPC. So the TypeScript code in your browser is actually speaking gRPC to the backend. The reason that's really interesting is because it means that the front-end developers can call backend services directly with a really well-defined like contract and type-safe interface that shows up with essentially like if the backend and the front end don't match, the code does not compile, which is a really great property for ensuring the correctness of the whole system. Another way we've gone deep on gRPC that you may find a lot of value in is in our use of interceptors. They're like middleware for gRPC, and they can run both server-side and client-side, which makes them more powerful than a lot of other kind of like middleware components you may be familiar with in like HTTP frameworks. At Ngrok, we use gRPC interceptors for many things. The most obvious is observability, but we've also adapted them to a number of novel purposes. When our dashboard invokes our gRPC backend, a sanitization interceptor like cleans out all the things that are internal and shouldn't be sent out to customers to prevent like security and data leaks. And we have like a number of other ones. There's one that I want to particularly show you that I think is interesting because it mentions something a little bit later, which is we have rich errors. So when you work with gRPC, you essentially get like 17 error codes and a status string to tell you like what went wrong. But often you want to send more error details than that. Like, can a customer see this error? gRPC supports doing that for you by allowing you to attach metadata to the error. But if you look at the documentation for how to do that, it's not the most ergonomic thing to work with. At Ngrok, we do something far more ergonomic. This is what our code looks like to send those errors across the wire. The way that we do this is we use interceptors to make this magic happen. We are returning our own error type there, and we're using interceptors to kind of like cheat it across the wire. The way that this works is that there is a client-side interceptor, which is extracting the error structure out of the details of the error and reconstituting it, unmarshalling it and type asserting it back to return to the caller. And then on the server side, you don't actually need an interceptor because the actual server-side stubs will try to type assert anything that is returned to them to see if they implement a particular function. And when they do, you can basically shove that error into the details to be returned back to the other side. So a very nifty trick that allows us to return errors in a really ergonomic way all across our code base, which is really critical to be able to properly surface user-facing errors from all upstream microservices inside of Ngrok. This talk title has infrastructure startup in it for a reason. The reason is that when you are an infrastructure software provider, other companies are relying on you. You are running their production infrastructure. And so if you go down, they go down. If you're slow, they're slow. So one of the many like architectural principles that I've really like grown fond of over the last 10 years has been figuring out how to make sure that we can handle these like hundreds, millions of operations a second while staying up and fast. And one of those ones is about how we deal with replication and caching. So in that example that we talked about earlier, the Ngrok agent starts up and it talks to our service and says, I would like to serve application on a particular URL. We have to check the database to say like, do you own this domain? What account are you in? Is your account suspended? And that's a great way to start and is how Ngrok started. But as soon as you start doing like thousands of operations a second, or in the case of our edge servers where they are processing millions, tens of millions, hundreds of millions of operations per second, hitting the database on every single one of those is a non-starter. So how do we get this configuration data to use in this hot path? We could shard and scale the database. That is a possibility. It is expensive to run that fleet. You could add a caching layer, but even network round trips are expensive. You could do in-memory caching, but as we know, one of the very hard problems of computer science is doing cache invalidation. It also has negative user experience effects, like your change may take 60 seconds to take effect, right? You've all seen that in various things that you used. Caching is why. So at ngrok, we use this other approach where we keep copies of highly queried tables in memory. What it looks like is our application services essentially creating subscriptions to the databases for the tables that they want, and then replicating essentially full copies of the tables into memory, so that when an operation needs to be processed, the application service just queries its local store instead of the database. What's functionally happening is that we are bringing the data to the compute. At ngrok, data plane services replicate nearly all of their queried data because for two really important reasons. The first is we cannot go down and we have to be fast. The thing to really emphasize here is reliability and speed are paramount. It has a number of other nice benefits. There are no cache invalidation problems. You don't miss the cache, and it will work as long as you have infinite memory. So there are downsides, right? But if AWS keeps adding instance sizes, maybe we'll all be okay. In terms of how we do this, there are any number of technologies that you can use to do this. The one that we use is particularly interesting, which is Postgres has a built-in mechanism where you can create a replication slot and essentially stream JSON changes for every single row out of the database. And so this is what kind of that beginning of that code looks like, to start streaming changes out from logical replication slots in Postgres to get JSON events of every row that has mutated. In the interest of time, I'm going to keep going here. Continuing on that theme of resiliency and fault tolerance, all of the greatest architectural design in the world will not save you if from the single biggest cause of downtime, which is humans. So how do we protect ourselves from the bugs that we write in our software? The easiest way is, of course, just to not ship bugs, but short of that, I want to know when ngrok breaks before our customers do. And since, I want to know that because bugs are going to make it to production. There was a time when I said they won't make it to production because I have tests and I continuously integrate, so they definitely won't make it to production. And that was because my worldview was based on lies. Lies like if the tests pass locally, they won't go to production, or if they pass in CI or in production, that they will continue to pass in production. They will not. To protect ourselves from this, at ngrok, we run all of our integration tests in production on repeat, 24/7, concurrently in a loop all the time. This is essentially what we do so that we know that when ngrok breaks before our customers do, most of the time. Bonus, it's also a free stress test. But the real important thing to recognize here is that your production environment is not the same as any other environment. It is not the same as it was 10 minutes ago because your users manipulated data inside of the production environment, and so it is different. It has different memory consumption, it has different topologies, it is never exactly the same, and that is why it is really important to be able to do that, and why we find it really valuable to run those integration tests all the time. Anyone have a visceral reaction to that? Of course, integration tests are supposed to make sure that things like this never happen, but inevitably, crashes do occur in production. The blue screen of death is really fun, but I don't want to actually talk about unexpected errors like the blue screen of death. What I actually want to talk about instead are expected errors, the ones you get when a user tries to enter an email address that's 1 gigabyte long, or they try to allocate more memory than all the bytes in the known universe, those kind of errors that you can expect and catch and handle. At ngrok, we have a very unique error system where every single user-facing error code in the system is defined in configuration, and we generate type-safe APIs and documentation for every error that a user could encounter in the system. This is a definition in our configuration language of what an error is. It has a name, it has a code, and it has like a message functionally. This is an example of like what one of those configurations looks like for a particular error that we call bindacl forbids name, and you can see kind of the template and the code that it gets. We do this for every single user-facing error. There are thousands of them. From that configuration definition, we code generate type-safe bindings to construct the error message. Here's what it looks like in the calling code where we like use it and return it. This error, by the way, if you remember that gRPC interceptor, it is generating that type that knows how to serialize itself and deserialize itself across the wire, so they transparently move between microservices. Why do we do this? There are many reasons, but let's start with user experience. When you run an ngrok command that hits an error, you will see something like this. And as developers, the first thing you will all do is type it into Google. And that's exactly why. Those error codes are meant to be completely unique strings that appear in Google as the top or only hit, which you'll see is there. And if you click on that link, you see a error page. That error page got created not because someone wrote it, but because we generated it from those definitions. For our most popular errors, the ones that users hit the most, we write our own documentation, we create videos, we add links to guides that all can get added to these error pages. It works if you like look at Google's like recommended search results. You'll see people searching for all kinds of errors. You'll see them show up in other places, other communities, so that users can coalesce and very quickly identify that someone has the same problem and understand how someone else solved it. And it also has tremendous value for support, who get email messages like support messages like these, and allows us to very quickly target how to solve a user's problem because we know exactly what problem they ran into. It's also really useful for just like product insights to understand like how are people using your system? What errors are they encountering? What should we fix? What should we make easier? The last thing I want to talk about with these error codes is that errors are an API for developers. I'm sure all of you who are writing Go often have done things like this and felt very sad, where you wanted to know what an error was, but you couldn't find out, and the only way you could do it was to check whether the string matched some string that you thought was correct. This is really brittle because someday someone's going to update that error message and your code's going to break. In that example from earlier, where we're using the ngrok SDK, really it kind of like boils down to like, if you caught an error, what do you do with it? Like, what should you do? And our error system means that we can basically make a unique error code of what happened available to everyone. So you can update your code like this to say like, great, tell me what code happened. And so then if I find this particular error code that we were looking at, maybe we try a different domain because we weren't allowed to use the one that we tried to use. Just recapping quickly, like, there are many, many benefits for why we build the error system the way that we do. The primary ones being mostly about supportability and user experience, about allowing users to very quickly identify what their problem was, solve it themselves, or help someone else know exactly what problem they encountered and solve it as well. Defining them this way also means you have language independence, so that you can like type generate these into multiple languages. We do this for TypeScript to generate similar errors in our dashboard, things like that. Before we close out, I want to talk a little bit more abstractly, other than these like practical concerns inside of Go, about some of the other things that I've learned about writing software over these last 10 years. One of which is, what language should you choose if you're building a new software startup, for example? At the beginning, when I was first building ngrok, I kind of ran through this, which was like, how do I build a web application that's real time, that's fast, it scales to many people, scales to like many, many simultaneous connections, it runs on all the cores of the machine, and I distribute it as a zero dependency binary everywhere in 2014. And at that point in time, really the only language that you could do this really well in was Go. And that's why I said this back then when I first built ngrok, that ngrok's success as a project is due in no small part to choosing Go as the programming language. That is kind of a rarity. These days, what I would say to you is if you're starting a new project, you should ignore all of that. Language choice kind of doesn't matter. Remember that they're massively like successful like software projects built in languages like PHP. No disrespect to PHP. Building software is hard enough. Like building a software business is hard enough. Like don't fight the technology. Pick the language you are most proficient in. Whatever you can get the most help with, whatever makes it easiest for you. That's what you should work with. Gonna leave you with two like quick things here. The first is when you are writing software, don't get attached to your code. Your software, the code that you write, is legacy code as soon as you're done writing it. Software is one of the most malleable building blocks on the planet, and the ecosystem changes all the time. Your requirements change all the time. You change all the time. Software is meant to be rewritten. One of the things that I've felt myself, and I think many folks have been like attached to the code that they write. These days, I try to remember that we are always building something new. We are always trying to focus on like what is a better solution. If someone hasn't rewritten the code that I've written, or I haven't rewritten it, then I get sad that it hasn't improved, right? Your code is always legacy when you write it. It can always be better. The last thing that I'll leave you with is that this community, like the Go community and the language community, is a fantastic community. It is welcoming. It is helpful. Being here, like this is a place that has been a great home for Ngrok, a great home for me, and a very privileged place to be in and to present to. So thank you all to all of you for being part of it, and thank you. Take care.